Water quality management for aquaponics. Water quality management is an extremely important, or possibly even the most important component of managing an aquaponics system. And the reason for this is that if we start with a fish, they live, they breathe, they breed, they eat, they excrete. Everything they do in the watery environment in which they live. Therefore, they are totally subject to the environmental conditions around them. They can't move themselves out of those conditions should they not be suitable. Furthermore, the plants as well are rooted in the water, and the temperature of the water, the pH of the water, the amount of nutrients available in the water, etc., all affect the plants directly. Therefore, it is critical that we as aquaponists understand water quality intimately and know how to manage and repair our water quality conditions for optimal growth of both the fish and plant crops. To start with, let's consider dissolved oxygen. Dissolved oxygen is extremely important to the health, the growth, the feed usage efficiency, and the survival of the fish. Furthermore, the plants are rooted in the gravel beds as well, or if you're using the raft technique, deep water culture, the plants are rooted directly into the water. In both cases, the amount of oxygen available to the plant roots is very important as well. It is important to understand that as the temperature of the water increases, the ability of the water to hold oxygen decreases. Similarly, as the altitude increases, the ability of the water to hold oxygen decreases as well. And what this means practically on a fish farm is that the higher the altitude at which you are positioning or erecting your farm, and the higher the temperature at which you're running the water for the plants and fish, the less oxygen is available in that water for the plants and fish at saturation. Therefore, the warmer the water, the more on top of our game we need to be when managing dissolved oxygen levels. Dissolved oxygen is replenished by means of aeration within an aquaponics environment. Also, the flooding and draining of the beds will contribute oxygen to the water and assist with removing carbon dioxide. This chart shows the impact of both water temperature and altitude on the amount of oxygen available for the fish in the water at saturation. If we have a look, for instance, and we assume that we are trout farmers, at a temperature of 16 degrees, which is about where we farm trout, the water will have about 11 milligrams per liter at sea level. But in Johannesburg at 2,000 meters above sea level, this drops down to only 8. Bearing in mind that the minimum acceptable level of oxygen for trout is 6 milligrams per liter, at sea level there's 5 milligrams per liter available for the fish to use, whereas at Johannesburg the same system design only has 2 milligrams per liter available, or 40% as much as is available at the sea. Clearly, altitude makes a huge difference. Similarly, if we regard ourselves as tilapia farmers, at sea level, there's about 9 milligrams per liter at saturation at 28 degrees Celsius. Whereas if we go up to Johannesburg, there's only about 7. Now, the minimum acceptable level for all fish other than trout is about 5 milligrams per liter. So at sea level, there are 4 milligrams per liter available for the fish at 28 degrees Celsius, whereas in Johannesburg, there are only 2 milligrams per liter. So in other words, in Johannesburg, you need to run twice as much water through the tanks to provide sufficient oxygen relative to sea level. Water temperature is also very important for both the plants and the fish for optimal growth. Fish and plants are ectothermic. The old term used to be cold-blooded, but in fact we don't use the term cold-blooded anymore. If the water temperature is 22 degrees, then the blood of the fish will be at 22 degrees. But equally, if the water is at 32 degrees, the fish's blood is also at 32 degrees, and that can certainly not be regarded as being cold-blooded. Each species has a wide survival range, but a narrow preferred optimal range for all water quality parameters, temperature being a good example of this. The optimal temperature for most species is towards the upper end of the survival range, even for a cold water species such as trout. Growth, immunity, food conversion, survival, and reproduction are all best near the optimal temperature for the species. The important thing for us as fish farmers to understand is that we must not stress the fish when adding them to our aquaponics system initially by changing the temperature rapidly. Equally, when doing water changes or adding water to the system, we mustn't rapidly drop or raise the water temperature. The clever people tell us no more than 1 degree decrease per hour and no more than 2 degrees Celsius increase in water temperature per hour for the fish to be happy. Bear in mind as well that temperature has interactive effects with all the other water quality parameters. pH, or proportion hydrogen. pH is a measure of the hydrogen ions in the water. It is logarithmic and it is negative. Therefore, it is represented on a scale without units from 1 to 14. 7 is neutral, less than 7 is acidic, greater than 7 is basic or alkaline. For aquaponics, a pH between 6.5 and 7 is ideal, although anywhere in the range 6 to 7 is regarded as being acceptable. The reason for this is that different nutrients and chemicals within the water are available to the plants at different levels according to the pH. If you have a look at this chart, let's start with nitrogen for instance. What you can see is that at a pH of 4, very little of the nitrogen in the water is available for the plants for uptake, as is indicated by the very thin line represented on that pink bar. As the pH increases right up to 6, there is a stepwise increase in the availability of nitrogen to the plants. Now, the concentration of nitrogen in the water has not changed. We're merely talking about the availability of that nitrogen. In other words, the ability of the plants to access that nitrogen. From a pH of 6 to a pH of 8, nitrogen is freely available to the plants. But a pH higher than 8, once again the nitrogen becomes locked out, as we say. And what that means is that although the nitrogen is still present in the water, because the concentration hasn't changed, it is no longer available to the plants. The plants can't access that nitrogen. If we go down this chart and we follow that same logic, you'll see that phosphorus is optimally available between 6.5 and 7.5. Ignore the top end. Potassium from 6 upwards, sulfur from 6 upwards, calcium from 7 upwards, magnesium 7 upwards, iron below 6, and so forth. If you have a look at the range of pH 6 to 7 and you drop down from the top to the bottom across all those bars, you'll find that all of them, except for aluminium, are highly available to the plants in that pH range, and that is why we maintain an aquaponics system pH in the range of 6 to 7. Aluminium is a poison. Aluminium is not plant food, and therefore the fact that it's available at a low concentration at that level is highly desirable. Hardness and alkalinity are related concepts. Hardness is a measure of the dissolved salts, especially calcium and magnesium, in the water. Alkalinity, on the other hand, is a measure of carbonate ions and bicarbonate ions in the water. Calcium and magnesium are required by both plants and fish for natural growth, whereas the alkalinity serves the purpose of buffering the pH. Alkalinity is a negative ion, whereas hydrogen ions are positive ions. As soon as additional hydrogen ions are released during natural biological activities within the aquaponic system, those hydrogen ions bind with free carbonates and bicarbonates. And that means the pH doesn't change because the hydrogen ions don't contribute to the pool of hydrogen ions within the water, and therefore the pH doesn't change. Whereas, if there's a shortage of carbonates and bicarbonates in the water, the hydrogen ions that are produced travel around in the water as free hydrogen ions. Bear in mind, the more hydrogen ions we have, It's a logarithmic scale. It's negative. Therefore, the lower the pH goes. So more hydrogen ions equals a lower pH equals acidic conditions. We do not want the pH dropping below 6. Therefore, we add alkalinity to buffer and stabilize the pH. Within aquaponics, we use either calcium carbonate or potassium carbonate to buffer the alkalinity. Nitrogen wastes. Ammonia is produced by the fish during digestion. The breakdown of proteins results in the release of ammonia, mostly from the gills of the fish, into the water. Ammonia is present in two forms, ammonia and ammonium. What we measure is in fact ammonium, but the toxic form is the ammonia. Ammonia is highly toxic to our fish, and we need to monitor the levels to ensure, especially during the early startup phases of the aquaponics system, that toxic levels are not attained. The proportion of toxic ammonia versus less toxic ammonium is a function of pH and temperature. In both cases, an increase results in an increase in toxic ammonia as well. Therefore, don't run the pH or temperature of your aquaponics system higher than it needs to be. The maximum tolerance level for most species of fish is a short-term exposure to an ammonia level of about 1 milligram per liter. In reality, at a pH level of 6 to 6.5, even as high as 7, within our aquaponics system, ammonia is not exceptionally toxic. It is reduced by means of either the biofilter if you're using deep water culture or nutrient film technique, or if you're using an aggregate bed or flood and drain mechanism, then the bacteria are housed within that gravel bed. Those bacteria consume ammonia and excrete nitrite. Nitrite is therefore also a byproduct of nitrification. These bacteria produce the nitrite. Nitrite is also highly toxic, and the acceptable level here is about 1 milligram per liter. Within the biofilter that the bacteria live in, where a nitrite is produced, a second group of bacteria lives symbiotically with the first group. They consume the nitrite and excrete nitrate. Nitrate is therefore the end product of this bacterial nitrification. It is not highly toxic, and the acceptable level is as high as 200 milligrams per liter. And in fact, we routinely measure levels of as high as 1,600 milligrams per liter within our aquaponics system. Neither the plants nor the fish appear to be at all stressed under those conditions. How do we get rid of nitrate within an aquaponics environment? Either if the levels get too high by means of water changes, but that is counterintuitive. Aquaponics is designed so that the plants take up the waste produced with the fish. If the ratios are correct, the plants should absorb all the nitrogenous waste produced by the fish in the form of nitrates, and nitrate levels should increase until they reach a point where the rate of production equals the rate of consumption by the plants, and the level will stabilize at more or less that level. Electrical conductivity, or EC as it is also known, is a measure of salts within the water, including the nutrients that our plants require. And it's very important to recognize that it's not only the nutrients, but it includes the nutrients. Therefore, we need to be very careful of false readings. A false reading would typically occur where the source water contains an elevated EC level, such that when you are measuring the EC in your system, you assume that to all be nutrients available to the plants, and it's not the case, because some of it is in fact raw water EC level. The ideal EC for your leafy greens is about 400 microsiemens per centimeter, whereas for your fruiting crops such as tomatoes, peppers, brinjals and so forth, a level of around 3000 microsiemens per centimeter is ideal. In our situation, we routinely measure EC levels in the region of 1000 microsiemens per centimeter. Knowing that our raw water has an EC reading of about 200 microsiemens per centimeter means that 1000 minus 200 equals 800 microsiemens per centimeter. It is a fair assumption to assume that that is about what is available for our plants, mostly as nutrients. Some of that will be the buffer that we add to the system, but the bulk of it will be nutrients. Carbon dioxide is a byproduct of respiration. Fish and bacteria consume oxygen, and plants also consume oxygen at night. And all three products then give off carbon dioxide. When the carbon dioxide levels within the water reach concentrations exceeding 20 milligrams per liter, this can create physiological problems for the fish. And we reduce the carbon dioxide by means of aeration. Hydrogen sulfide occurs wherever we have fermentation taking place within water. Fermentation occurs under anaerobic conditions where organic material has accumulated, it's colonized by bacteria, the oxygen is rapidly used up, and then a second set of bacteria that are anaerobic bacteria convert the organics into various products, including hydrogen sulfide, which is extremely toxic to our fish. Therefore, we need to avoid the settling of any solids within the system, and particularly do not allow the beds to block, which is one of the reasons why we use 20 millimeter stone rather than sand or refined gravel. Okay, so we've discussed water quality. We know what the levels are that we're looking for, and we have an idea of which parameters are important to manage. How do we actually measure the water quality within the system? Essentially, there are three tools we can use. The first option is a test kit. Now, a test kit is based on a mix of chemicals that gives either a color change or an absolute color. Look for titrations, look for liquid-based kits, as these are the simplest to use. Test kits are fantastic. They're quick, they're simple, they'll give you a fairly accurate answer, but they are not very accurate. So if you are dealing with a sensitive species of fish such as trout, you may find that a test kit doesn't give you enough advanced warning of a problem that is developing. However, if you're dealing with catfish, tilapia, carp, one of the many other species, then test kits are perfectly acceptable. The next option is a meter. Meters are more expensive than test kits, but they are significantly more accurate. For instance, if we're measuring pH with a test kit, it may tell us that the pH range is between 6 and 6.5 or between 6.5 and 7, whereas with a pH meter, it will give you an accurate answer to the second decimal point. Spectrophotometers are also very expensive, but they are also very accurate. And an advantage of a spectrophotometer is that no calibration is required. However, this is not a perfect world, and spectrophotometers also have their disadvantage. And the big downside with them is that they are very slow to operate, and the reagents are expensive. So they're actually very slow and expensive to operate. But if you are managing a system with a sensitive species, that may need to be your choice if you're going to manage the risk adequately. When designing a system and when managing a system for aquaponics, we will, by the very nature of things, have three ingredients that we are managing for. The first is the bacteria, because they do the bulk of the work, converting the fish waste into plant food. The second is the plants themselves. They are very important because that is where the bulk of our income comes from. And the fish are the third component. They are the engine that drives the system. We feed the fish waste in the water, and that produces the food for the bacteria and in turn for the plants. The fish, in addition, also provide a supplementary source of income. However, it is more than likely that you'll find that the ideal conditions for the bacteria are not the same as the plant crop that you're wanting to farm, which is not the same as the fish within the system. A degree of compromise will be required. We will discuss this in more detail a bit later. Generally, what I propose is select your system design according to the requirements of the plant crops you're wanting to produce, because that's where the bulk of the income will come from. And then, having selected the plant crops and the system design, select your fish species to match. Testing water quality. This chart provides a very useful first step guide to which parameters need to be measured, how to measure them, and what frequency to measure them on. Now, bear in mind, I will often mention new system or mature system. In a new system, these levels have not yet stabilized. The fish production is not yet stabilized. We don't have a completely fully stocked system. Therefore, we need to be more pedantic during the early days, and early days I mean the first 2 to 3 months, than we do once the system is more mature and tends to be more stable. Let's have a look at dissolved oxygen first. The optimum is a level of more than 5 milligrams per liter. The minimum is a level of 5 milligrams per liter. We do not want the oxygen dropping below 5 milligrams per liter, as this will compromise the ability of the fish to grow and to utilize the food efficiently. The technique used for measuring oxygen, I strongly recommend that you use a dissolved oxygen meter. In my experience, spectrophotometer and test kit readings are so inaccurate as to be of very little value. The frequency should be daily during the early days of a new system. Once the system is mature and once the aquaponist understands what's going on, you will find that monitoring the behavior of the fish will be your first warning sign that the oxygen levels are compromised. And at that point, you can ad hoc investigate the oxygen levels if you suspect there might be a problem. The temperature required is species specific to the plants and as a result to the fish. I propose measuring it by means of a maximum minimum thermometer, or measuring mid-morning and mid-afternoon, or measuring first thing in the morning before the sun shines on the tunnel and then mid-afternoon to get the minimum and maximum temperatures for the day. I also propose measuring water and air temperature and recording both separately. This should then obviously be done daily or twice daily. pH, the optimal is about 6.5. The minimum is 6.0. The maximum is 7.0. The technique for measuring pH, a test kit is perfectly acceptable. It gives you an indication of what range the pH is in, and that is in fact acceptable. If you're wanting a very accurate reading, such as we prefer to do in our system, a pH meter is required. The frequency there is daily, and I recommend measuring it daily at the same time. Electrical conductivity, the optimum for leafy crops is about 400 microsiemens. The optimum for fruiting crops is about 3000 microsiemens. The minimum for any sort of commercial plant growth is going to be in the region of about 200 microsiemens. The maximum for any crop shouldn't be much beyond about 3000 microsiemens. For measuring electrical conductivity, we use an EC meter and we measure that daily. The ammonia should ideally be below 0.1 milligrams per liter. There is no minimum. An ammonia level of 0 is the theoretical minimum. The maximum is about 1.0 milligram per liter. A test kit is perfectly acceptable for measuring ammonia. If you want accuracy, use a spectrophotometer. And once a week is adequate for you to manage the ammonia levels within the system. Nitrite is exactly the same. The optimum level is less than 0.1 milligram per liter. There is no minimum. And the maximum is about 1.0 milligrams per liter. A test kit is accurate enough for aquaponics, but if you want a more accurate reading, use a spectrophotometer. And that should be done preferably weekly. Certainly with a new system, it should be done weekly. But once the system is mature, a monthly nitrite reading is adequate. Nitrate, the optimum is about 50 milligrams per liter. And I'd put a question mark behind that. We don't yet know accurately what the optimal nitrate level is for an aquaponics system. The industry is too new, and at this stage we're still answering lots of questions. The minimum is about 20 milligrams per liter. Below that, I can't believe that you're going to get much plant growth. The maximum is about 200 milligrams per liter. Now, this is in terms of what the textbooks advise. As I already indicated, we routinely run our system at nitrate levels of about 1,600 milligrams per liter. And the fish are delighted, they feed well, they grow well, and the plants do well at those levels as well. So I would put a bit of a question mark around optimal nitrate levels. I think it's probably a lot higher than has been suggested here. How do we measure nitrate? A test kit is perfectly acceptable, and that should be done about once a month. Hardness, the optimal is about 50 milligrams per liter, the minimum is about 20, and the maximum is about 150 milligrams per liter. This is measured by means of a test kit, and again, once a month is adequate. Alright, so we measure our various readings, and we find they're not what they should be. How do we manage the water quality to remain within the optimal levels we require for our fish? Well, firstly, temperature. If the water is too cool, we need to heat it. If it's too hot, we need to cool it. In the summertime, we can open the doors of the tunnels to vent cool air through the tunnel and get rid of the warm air, and we can run cold water through the tanks in an emergency. But this should only be done in an emergency because we don't want to dilute the nutrients. If the temperature is too cool, or in winter time, what we can do is run the water through a long length of black piping or other passive form of heating if we are adding new water to the tanks, so that the new water comes in warmer than the ambient water during the winter months. If the pH is too low, we need to manage it to prevent it dropping below 6.0. Calcium carbonate and potassium carbonate are generally added on a daily or every other day basis in a commercial system to maintain the pH, preferably in the region of about 6.5 pH. We have found within our system that calcium carbonate is added at a concentration of about 10 grams per kilogram of feed, or about 10 grams per cubic meter per day. And in that way, we manage desirable pH levels. Bear in mind as well, if you're finding that your pH is climbing unexpectedly, this could well be a result of the beds being blocked somewhere within the system. Under these conditions, we get anaerobic activity, and this causes the pH to rise rather than fall, and this is a good early warning sign that somewhere a bed may be blocked. If you find this happening, be sure to identify where the bed is blocked and clean the bed thoroughly so that it does not poison the system. Also, if you find that the gravel that you have used in an ebb and flow system is a source of alkalinity, be sure to change this gravel, and therefore always test the gravel before using it within the system to avoid the situation where the gravel is causing the pH to rise undesirably. Electrical conductivity. If the ratios of plant beds to fish is not correct, then the EC will also not be correct. If the EC is too low, there are insufficient fish within the system. If the EC is too high, there are insufficient plants relative to the amount of fish. If the EC is too high, one can do a water change to reduce the EC level and limit the stress that the fish are exposed to. If the oxygen levels are below 5 milligrams per liter, especially if the fish are breathing heavily or gasping, then be sure to increase the aeration to each and every tank. If this is a continual problem and you can't increase aeration further, the other option is to reduce fish densities. If the ammonia levels are too high, ask yourself, are the ratios of fish to plant correct? Or, if you're using a biofilter, is the biofilter big enough for the amount of feed going into the system? You can temporarily reduce feeding and also ensure that the beds are not blocked. In an emergency, one can do a water change to dilute the ammonia, but bear in mind this again dilutes all the other nutrients available to the plants. Biopond can also be used in an emergency to reduce ammonia levels. If nitrite levels are increasing, suspect that the beds are blocked somewhere, or if you're using a biofilter, that the biofilter needs cleaning. If you find your nitrite levels are increasing, you can once again temporarily reduce feeding. and in an emergency you can do a water change. Personally, I prefer to add biopond, as this means that we don't lose the nutrients from the system, but the biopond does neutralize the nitrite toxicity by converting it to nitrates. If the nitrate levels are too high, and I've already indicated we don't yet know what too high actually is, but if you find your nitrate levels keep climbing and the fish are becoming stressed, then again it indicates that there are too many fish relative to the amount of plants within your system. If the fish are stressed once again, one can do a water change. Thank you.